Welcome to the AI Research Roundup. I am Alex. Today, we're looking at a paper from May 30th, 2025, titled AReaL, a large-scale asynchronous reinforcement learning system for language reasoning. This paper presents AReaL, a system designed to significantly speed up how large language models learn complex reasoning tasks using reinforcement learning. Now, reinforcement learning is a method where models learn from the data outputs, or rollouts, they generate. Many current systems are synchronous, meaning generating these rollouts and then training the model happen in slow, alternating steps, which can be inefficient. AReaL, however, is fully asynchronous, so data generation and training can run continuously and independently. It also cleverly manages data freshness, ensuring stable learning, and achieves up to 2.77 times faster training, with matched or even improved final performance. And for those interested in the practical side of this AReaL system, the researchers have also made their work open source. They've released the AReaL repository, which provides their distributed and fully asynchronous reinforcement learning training system for large language models. This repository includes example scripts, evaluation tools, and training recipes, so you can dive into the implementation. Alright, so to give you a visual of how AReaL manages this continuous workflow, Figure 3 shows its interruptible generation feature. We see timelines for 3 GPUs. GPU 1 and GPU 2 are busy generating data, shown as light blue bars. GPU 3, meanwhile, is handling the training, shown in orange. The crucial part is when new model parameters, which are the internal settings or weights of the AI model that are adjusted during training, become available. The generation tasks on GPU 1 and GPU 2 can be briefly paused, indicated by yellow load weight segments and blue interrupted sequence markers to update the model. Then they just pick up where they left off. This keeps all the GPUs working efficiently. We also see green segments for KV cache recompute. The KV cache is a key-value cache that stores intermediate computations from the attention mechanism in transformer models, speeding up the generation of subsequent tokens. This recomputation is needed after an interruption to ensure consistency. Now, to contrast with the efficiency we just saw with AReaL's interruptible generation, Figure 1 really highlights why older approaches can be less efficient. On the left, we see a typical synchronous system. Here, multiple GPUs, GPU 1 through 4, are doing generation, shown by the blue bars. But then, they all have to stop and wait while training. The orange block happens. This means those generation GPUs are idle. The right side shows a one-step overlap system. It's a bit better, as generation on GPU 1 and GPU 2 can happen while GPU 3 and GPU 4 are training. However, you can still see potential idle times for the generation GPUs, waiting for new model parameters after each training step. Both setups clearly lead to underutilized inference devices. Okay, so building on that idea of efficient interruptible generation we saw earlier, Figure 2 gives us a broader look at the entire AReaL architecture. On the left, the generation side features those interruptible rollout workers. They receive prompts from a rollout controller, which coordinates the whole process. These workers generate trajectories, essentially sequences of model outputs, which are then assessed by a reward service. These evaluated trajectories are stored in a replay buffer. Then, on the training side, trainer workers continuously pull data from this buffer to update the model's parameters, which are managed by a parameter service. This asynchronous loop ensures constant activity. Now, with an asynchronous system, training effectively with potentially stale data is key. Figure 4 shows AReaL's policy optimization math. A policy is the AI's decision strategy. AReaL adapts proximal policy optimization, or PPAGE-O, an algorithm that improves this policy in stable steps. Equation 4 is a standard PPO objective, J of theta, using an importance ratio to adjust for older data. Equation 5 details AReaL's innovation. It couples policies. It uses a more recent proximal policy as a stable reference. This helps keep updates within a trust region, crucial for reliably training with that stale data. So, that decoupled proximal policy optimization helps AReaL handle stale data effectively. And this efficiency really pays off when we look at system performance. As shown in these next set of plots, also labeled Figure 4 in the paper. These graphs compare AReaL's throughput, basically how many tokens it can process per second, against a synchronous system called VRL as we increase the number of GPUs. Alright, we're looking at 6 different scenarios here with varying model sizes from 1.5 billion to 32 billion parameters and different context lengths, which is the maximum number of tokens, or pieces of text, the model can consider at one time. In every case, AReaL, the blue line, achieves significantly higher throughput than VRL, the orange dashed line. Notice how AReaL's performance scales much more closely to the ideal linear trend, shown by the dotted black line. What's particularly telling is that for the largest model, the 32 billion parameter one, with a long 32,000 token context length, VRL actually fails to run. Its data points are missing, likely due to out-of-memory errors, while AReaL continues to scale well. This really underscores AReaL's robustness. Okay, so those impressive throughput gains we just saw translate directly into faster end-to-end training, which Table 1 here clearly shows. This table compares performance on the AIME24 math benchmark and the live code bench for coding tasks. For the 1.5 billion parameter math model, AReaL achieves 42.2% accuracy in just 14.8 hours. That's much faster than a leading synchronous system, shown as W/VRL in the table, which needed 33.6 hours for similar accuracy, and also faster than AReaL's own synchronous version. Similarly, for the 14 billion parameter coding model, AReaL reached 58.1% accuracy in only 21.9 hours, again, significantly outpacing synchronous methods. This really highlights AReaL's efficiency in reducing training time while keeping accuracy high. Okay, so those impressive throughput gains and faster training times we just saw are a result of several innovations in AReaL. To understand the impact of specific design choices, the researchers performed ablation studies, which essentially means they tested the system with and without certain features to see how much difference they make. Figure 6 here shows one such study, focusing on the benefit of interruptible generation. This bar chart compares the average throughput, measured in tokens per second, for 2 different model sizes, a 1.5 billion parameter model and a 7 billion parameter model. The blue bars show the throughput with AReaL's interruptible generation, meaning the process can be paused to load new model updates, while the orange bars show throughput without this feature. For both model sizes, interruptible generation clearly performs better. It leads to a 12% throughput increase for the 1.5 billion model and a 17% increase for the 7 billion model. So this feature significantly boosts how quickly the system can process data. So that boost in processing speed from features like interruptible generation really highlights the core advantage of AReaL. Its innovative asynchronous approach dramatically speeds up how we train large language models, especially for complex reasoning tasks. This kind of progress is crucial for building more capable and efficient AI systems. Thanks for tuning into the AI Research Roundup. I'm Alex.